Hey guys, hope you're all doing well. This is my chapter 3 video on acids and bases and how you can use different factors, including the atomic size, resonance, induction, and orbitals to determine what is the stronger acid you're looking at. So let's get started. First of all, a little review on Gen Chem stuff. So this Bronson-Lowry acid base, you're probably familiar with. It's the loss and gain of a hydrogen plus. And again, an acid is a donor of it, so it gives away an H plus, and a base wants to accept it. So I have an example here with the kind of arrows that you'll see for these reactions. So you have the acid here, which likes to give away that hydrogen, and you have that base that wants that hydrogen. All right. So talking about the stability of acids, so the stability of those that give away an H plus, there's two ways to really assess the strength. One of the ways is looking at the pKa values, and I said that was the quantitative way. That gives you a definite number that you can put to determine what has the bigger pKa value. But the qualitative way, and the way I'll be talking about, and your lecture will be talking about, is ARIO, which stands for the atom strength and electronegativity. That's this En, the resonance, induction, and the orbitals it has. So this is the qualitative way to determine the strength of different acids, or the stability of different acids. So I'm going to go through each one of the ARIO of ARIO, and let's start with A. So the atom size and electronegativity. For this one, I said please use the periodic table. For an exam, you're definitely given a periodic table. So remember that the electronegativity runs left to right and bottom to top. So I believe, I have a periodic table here. So again, electronegativity goes from left to right and from bottom to top. So, and if you look at the atom size, it's just, again, in these little boxes. So that's really easy. So an example I have for this one is to compare the two protons that are shown in the following compound. Which one is more acidic? Okay, so to determine this, we actually want to take both of them away and see what happens when we take one of them away. So let's do that. For this first one, we have this red hydrogen. So let's take away that and see what that gives us. This stays the same over here, but now we're left with a negative right there, which you'll always be left with lone pairs and a negative formal charge, because you're losing that hydrogen. You're losing that electrons with that hydrogen. So that's what that would look like if you lost this red hydrogen. Let's look at what it would look like if you lost the blue hydrogen. Whoops. Now we got 3 sets of lone pairs and a negative charge on this oxygen. Now we can look at which one is more stable. And I told you guys this first one, the atom size and electronegativity, the larger and more electronegative the atom is equal to how stable it is. So if you have a larger atom or a more electronegative atom, it's going to be more stable, and vice versa. So we really want to rank the stability of, again, this nitrogen and this oxygen. Which one would be more stable, and subsequently, which one would be more acidic? And that would be the oxygen, because if you look at a periodic table, the oxygen is not only bigger in atomic size, but it's also more electronegative. Right, because it's more to the right. So it's more electronegative, it's a bigger atom, so therefore it would be more acidic. Okay, so we got that out of the way. That's A. Another way to determine if an atom is more stable as a acid is by resonance. And you guys dealt with resonance in your previous chapter, so you're good at resonance structures, and you can determine from resonance structures if your compound is more acidic than another compound. So let's do that. We have these two structures right here. We have ethanol and acetic acid. And again, we're going to do the same thing that you do with these acids. You take away that hydrogen. So let me show what this would look like if you take away both of these hydrogens. Again, you're going to have a negative formal charge for both. Now, which one would do more resonance off the top of your head? It would probably be this one, right? We have a pi bond connected to a negative charge, so we can put, let me just do a quick resonance structure. We can put one lone pair here and then push this pi bond up into the oxygen to give you resonance. I'll show all the lone pairs. So this has two resonance structures, right? We have two resonance structures. This one, can you do any resonance? Let's see. Let's see if there's any plausible resonance that we could do. Now, I bet one of you that's watching this video is like, well, you can probably put one of those lone pairs on there, and that's technically a resonance structure, right? But it's not. You have to make sure that you have all the formal charges the same. So for this one right here, we had a -1 formal charge in the first one, and we have a -1 formal charge in the second one. For these two, though, you have a -1 and you have a neutral. You have a 0 formal charge in that second resonance structure. So this is not a plausible resonance structure, meaning that you can only do one type of resonance. So since this one can do two, acetic acid can do two types, has two resonance structures, it's therefore more acidic. It's more acidic, it's more stable as an acid. Okay, so that's R. We went through atom size and resonance. Let's go to induction, which is a pretty new term that you guys will learn in organic chemistry. It's basically, you know, what I wrote right here, halogens, so chlorine, bromine, any other halogen creates this inductive effect on the compound, making it more acidic. So I gave you guys the pKa values to compare all of these. Remember, the smaller the pKa value, the more acidic it is. So since this one has a bunch of halogens, a bunch of chlorines, compared to this one over here, which has no chlorines, that is therefore more acidic. And this will be really apparent in any practice problems or test problems, what they're trying to go for here, because they'll have a bunch of these chlorines or bromines on these structures, and you'll be like, oh, that's induction. So you can kind of guess that that is more acidic. And again, why is that the only difference in these? Because all these structures are the same, except for the amount of chlorines that you have. So you have two oxygens, you got a carbon, a hydrogen. Those are all the same, but it's just the chlorines that differ between each of these, therefore giving you, a more acidic compound. The more, halogens you have attached to it is more acidic. And the last one in ARIO, is orbitals. So we went through atomic size, resonance, induction. Last one is orbitals, which you guys have already kind of learned the ranking of acidity when you talked about resonance a little bit. But for the ranking of stability with and more acidic acids is triple bonds. So again, sp is triple, sp2 is double bonds or pi bonds, and sp3 is single bonds. So in the last step of ARIO, if you have a triple bond, it's going to be more acidic than a single bond. So for this example right here, we have a blue hydrogen and a red hydrogen. Let's determine what the orbital that it's currently occupied is in. So this one, this hydrogen is connected to a triple bond. So this is going to be an sp hydrogen. And this red one, it looks like it's connected to a double bond. So that's going to be sp2. This sp triple bond is more acidic than the sp2 double bond. And if you wanted to pull, let's say we wanted to determine this hydrogen as well, this hydrogen is connected to this carbon, and that carbon is single bond, so this would be sp3. So that sp3 hydrogen would be less acidic than the sp. So that's ARIO, again, ARIO. And let's see what the next slide is. So ARIO, an important thing to note is that ARIO is in that order. So what I wrote here is that even if one compound has maybe a better inductive effect, if the compound has better resonance, it will be more acidic. So let's say we have these two compounds. We have one, let's say we have a hydrogen, and then we have another one with nitrogen. I came up with this on the fly, but let's say we take away, so there's a hydrogen. So we take away both these hydrogens. Even though this nitrogen could resonate up here, let's say there was an oxygen, even though it could resonate, that R is lower than that A. So because oxygen is a bigger atom than nitrogen, that A overrules the R. So it goes in that order. So you really want to look at the atom size before anything else. If oxygen is bigger than nitrogen, even if nitrogen can resonate, this first structure will be more acidic. And I'll be going through some practice problems in a second on that. So that's a really important thing to note, is that it goes in order of ARIO. Okay. The one exception to this is if you have a hydrogen or a compound that has a triple bond, that outranks anything in the ARIO, and that's really the only exception you'll learn in organic chemistry. There's other exceptions but this is the only one you really have to go over. So sp will overrule anything, even if the atom size in a different compound is larger than a carbon. Let's say you were dealing with an oxygen versus a carbon. If that carbon is triple bonded and the other carbon has a hydrogen, this one would outrank that the size of the atom. So that's the only exception there. So I have this practice problem. This is a pretty good problem. It asks which is more acidic, and it goes through, it highlights the hydrogens it has there, and it asks what is more acidic. So I thought I would go through each of the ARIO and determine what the differences are between these. So let's start with A. Remember, A is atomic size. So let's see, if you take these hydrogens away, what is it attached to? They're both attached to oxygen. So that's the same. We don't have to worry about A because they're both attached to oxygens, right? So that's the same, atom size. So let's go to resonance. Can these resonate with each other? This first one here, I can rewrite this. For both, if you take away both of these, let's see. So this first structure is taking away this hydrogen and making another, lone pair with a negative charge. What can that do? That can resonate, right? Because you can put that lone pair on that bond and you can push this double bond up like we have been, and that can resonate. It has two resonance structures, right? because that, the charges would stay the same because this would end up having a -1 formal charge. So for let's say for the red hydrogen, it has 2 resonance structures. Let's see if we can do the same thing with the blue hydrogen. Let's see if we can do that. Because if we can't, that's a great depiction at which one is more acidic, because then we can stop there. Remember, it goes in order. So if you have, if you don't see any triple bonds, of course, but if we have no resonance on this blue hydrogen, then we know that this one has to be more acidic. But let's look. Let me rewrite everything the same way. Again, the C is just like that. I'll rewrite it like that. Can we do any resonance? Of course, this hydrogen would be taken away. So I'll show all the lone pairs and we would have a negative right there. The only way you can possibly resonate is pushing this lone pair in, but that really wouldn't do anything. You'd be violating this carbon's octet rule, and you just couldn't do that. So this only has, that structure of a negative formal charge there. It has no other resonance structures. So that means that this hydrogen is more acidic than the blue one. So we can stop right there because, of course, the inductive effect is lower than resonance, right? It's lower. This is 1, 2, and inductive effect is third, and then the orbital is fourth, unless you have that sp triple bond, which we don't. Since that inductive effect is third, and the resonance outranks that, we can just stop right there. Okay, hopefully that makes sense. I have some other problems that you can feel free to pause the video. I'm gonna go through them fairly quick, I would say. But feel free to pause the video, and then when you're ready, you can unpause it and see if we get the same answers. So for this first one, for A, what's the first one in ARIO? I'll rewrite it, ARIO. The first one is atom size. This one is connected to an oxygen, and then the blue one is connected to a carbon. So right away, I would say that the red hydrogen is more acidic than the blue one, because we're not dealing with any triple bonds, so we can cross out that orbital, no inductive effects, and no resonance, because in our A, in our first priority, we already have a difference. So that difference is the atomic size. So that oxygen is more, it has a bigger size and it's more electronegative than that carbon. So for this answer, it's the red hydrogen. All right, moving on to the second one, we're gonna use the same idea of ARIO and see if we can guess or determine what the stronger or what the more stable acid is. So let's get started. So we have this red one and this blue hydrogen. If you took both of those away, what would it be connected to? It looks like it would both be connected to carbons. So that is not a difference we can make there. The other two right here, we have induction. If we want to skip resonance because we don't know yet. If we want to look at induction, those are the same, right? There's no double or triple bonds directly connected to those hydrogens. So these both would be sp3 and sp3 hybridized. Looking at the orbitals, or I'm sorry, I kind of went too far. That's for the orbitals. So the sp3 would be for the orbitals. But induction, again, there's no difference as well. There's no halogens connected to this molecule. So induction is not a factor either. The one factor that we couldn't rule out just by looking at this compound is resonance. How does resonance play a factor in this? And I will actually rewrite this compound twice to see if we took, one or the other hydrogens away, what would happen. So for this first one, we'll call this 1, and we'll call this 2. For this first one, let's look at the red. So if we took that red hydrogen away, we would have a lone pair with a -1 formal charge. And that could resonate, right? We have a pi bond up here that could go up there, another pi bond that could go up there, and this could resonate on either side. Obviously, there would be different steps, but you can find 3 resonance structures from this. So if we went, let's say we took this lone pair on this bond, and then that double bond goes up like that, that would make a resonance structure. Or we could put the lone pair on the other side, and that pi bond goes up there. So that's 3 resonance structures that we can make for this first one. I'll just include all the arrows here. So that's 3 resonance structures. So red has 3 resonance structures. Let's see how much blue has. So blue, if we took that hydrogen away, lone pair on that end carbon on the right, could this do resonance? Yes, it could. We could put this lone pair, just like we did for this one right here. We could put it up onto that bond, and we could push that pi bond on, but we can't do anything besides that. So the blue only has 2 resonance structures. The red has 3. So again, the more resonance you have, the more stable it's going to be. So our answer is this red hydrogen is more stable because it has more resonance structures. All right, let's look at C. A big thing to note here, again, let's rewrite ARIO, is we have hydrogens on different atoms. So we have a hydrogen connected to a nitrogen and a hydrogen connected to an oxygen. Right away, we can say that this A in ARIO is different, and it should signal that this hydrogen is probably going to be more stable as an acid, right? Because oxygen is bigger and it's more electronegative than nitrogen. If we want to go down the list, resonance doesn't play a factor because if you already have a difference in that A, that outranks anything else. It doesn't look like we have any induction factors or any orbitals directly connected to those hydrogens. So that hydrogen connected to the oxygen will be more stable than the hydrogen connected to the nitrogen. All right, let's move on to D. Let's rewrite our ARIO. Okay, let's look at the atoms it's connected to. So it looks like both of these are directly connected to carbons, so that's not a difference. We can go on to our next one, resonance. Let's call that a blank for now because we would have to obviously see. No induction factors, we don't have any chlorines or bromines, but the O, the orbitals, are different as well. So how is this hydrogen different from this one? Because the red hydrogen, so I'll put the red hydrogen is an sp2 double bonded carbon that it's attached to, and the blue hydrogen is sp3. So that's one difference, but we didn't really check out the resonance. So let's do that. Okay, so let's say for this first one, I'll write it twice to see what would happen if we took away both hydrogens. So for this first one, we couldn't do any resonance there, right? Because it's a localized lone pair. It's directly connected to that, that double bond. So we couldn't do any resonance there. For the second resonance structure, we can do resonance though, right? We have this lone pair that can come up to this bond, and then this lone pair can come up there. So what would that second resonance structure look like? Something like a double bond right here, And we have, let's see, lone pair right there, and that nitrogen does not have 3 bonds anymore, so that is a negative charge right there. So even though we have a difference in orbitals, since our resonance prefers, more resonance structures is more stable, that means that this blue hydrogen is going to be more stable. Okay. This one right off the bat, it's going to be this one, right? Right off the bat, this A in ARIO, difference in atoms. We have a nitrogen and a carbon. That nitrogen is more electronegative and it's bigger than that carbon. So we can say that right off the bat for that one. Going on to this next one, again, we have a difference in electronegativity and a difference in atoms. Now, sulfur you might not be familiar of. I'll go back to the periodic table. Sulfur is bigger than oxygen. So that should signal that, the bigger the atom size is the one we want to pick to be the more stable of an acid. So this blue hydrogen, that blue hydrogen is going to be more stable. It's going to be more acidic. All right. And that is the end of this video. I hope this video helped. Again, if you do enough practice problems, you'll really get the hang of it. And I will see you guys in the next one.